Alright, hell yeah. So we're going to go over the torsion derivation. And this is pretty sweet because I actually haven't made a video, a math and physics video with this camera for quite a while. So hell yeah. And let's see how we do. Trying to go faster, but still keep it real. We're doing material mechanics, and you still need to start with the basics. And I literally am going to always start with a steel bar that's 1,000 millimeters or 1 meter. And I'm going to have it have dimensions of 1 inch by 1 inch. You know what I mean? We're mixing units, but this is just something that I can visualize very easily. Cool. Material mechanics says that if I hand you this and it's made out of steel, it has strength. And I can just give you the number. If I say 58,000 pounds, hell yeah. You know, like an almost full semi weighs 58,000 pounds. So you could literally, you know what I mean, hold up a semi with this steel rod, if that was your objective. Cool. And then material mechanics, well, let's go to the other thing, because that is a force. And then the other kind of, I would say this is the nuts and bolts of material mechanics, is that when you do use this to hold its max, and I can do a little subscript here, that's going to be the max force you can get out of this chunk of steel that I just gave you. When you put this on, you know, something heavy that weighs 58,000 pounds, this bar is going to stretch out. So it's going to go from its original length to, you know, maybe a little bit stretched out. And so this bar can only, I'm going to say only, you know, air quotes, stretch 2 millimeters. And so we have this relationship between the length of the bar that I gave you and how much you can actually visibly stretch it. And this is the bummer about material mechanics as well, is that materials are linear. We call this linear. Have a linear range. But I'm going to say that's where all the strength comes from. It's a huge, you know, just a mental assumption, but if you say all strength comes from that linear range, you're not going to build things where people are going to die. You know what I mean? And basically, pretty much all the strength does come from what we call the linear range. And what we know about this linear range is that you can't stretch a material very much. You know, if I hand you a 1 meter steel bar, you can stretch it 2 millimeters. You would barely notice that. And hooking this thing up to a semi is serious business. You know what I mean? If you got air underneath that semi, that's a lot of load. And I don't know. And this bar only stretches 2 millimeters? Yeah, well, okay. So that shows you that, yeah, those distances are real small. Sometimes you can't even see them. They're there. Cool. That's where I do need to mention that if you put more weight, you know, if you load this thing up with more weight, what's going to happen? Well, steel can lengthen up to 30%, an extra 30% of its length. Hey, that's 300 millimeters. So this is the hugest discrepancy in material mechanics that can be confusing. You're like, at one hand, if I'm trying just to use the material and not get anywhere close to killing people, I'm going to be in that linear range where I'm just not going to see any change in length. But these materials can change in length, especially steel. It can go plastic, and it can stretch 30%. You know, sometimes only 5. I would say 5 to 30. That's got to be a perfect specimen. But even 5% is 2 inches. That's 50 millimeters. That's significant. You could see that. You could see the steel bar stretching 2 millimeters if you just kind of put like a meter stick up against it and then had this thing loaded. You would notice that. Cool. All right, so that is that. So for this video, though, I'm going to say the upper limit when this gets to 2 millimeters. When we get to 58,000, I'm just going to mentally say something broke. You know what I mean? That's when something broke. That's when someone lost their lives. So we have loss of life. Hell yeah. I think making this significant as an engineer is useful, because when we get into the derivations, we're gonna use this is F max. This is the first term that you could tell someone to be like, hey, I just handed you something and there's going to be a max on the force. If you choose to have a bigger number than this force, you're going to kill people. I think, you know what I mean? Your thing is going to break, or you're going to kill people, or both. Even though in a lot of applications, you know what I mean, maybe the bridge just sags and you get into this range of, like, you went from just a 2 mil change in length to maybe just a 1%. Hey, it's not going to break. Things are going to break when they get to this 5 to 30%. But if you put another 1,000 pounds on this, let's say you put another 20,000 pounds on this thing. There's a chance. And then that is also the crummy thing about material mechanics, is when you actually put more load, if you get into that plastic range, hey, your steel becomes stronger. Where this thing can maybe take 70 up to 80,000 pounds, maybe. Let's just say 70,000 pounds. But, so now here's what I'm saying. If you apply more, if you're going to put 80,000 pounds on this, it for sure is going to break. There is no magic, there's nothing magical after loading something past what the number in a force that it can take. Hell yeah. Alright, so now I'm going to hand you this bar, and I'm going to say 2 millimeters. And it just doesn't have the same ring, does it? I hand you this steel bar and I say 58,000 pounds. You're like, sweet, I kind of know what the hell's going on. If I hand you this bar and say 2 millimeters, how are you even going to perceive that? How are you going to measure that? But let's say I did give you a little strain gauge and we taped it on there with the electricity, and I gave you a little readout. And then so when you're using your steel bar that I gave you, this is constantly, showing you a readout, and maybe you got an earphone in your head that is constantly telling you what the change in length is. You know what I mean? So it's like 0.5 millimeters, and then it tells you it's 0.7 millimeters, and then 1 millimeter, 1.5 millimeters, and then it gets up to 2 millimeters, and you'd be like, hey, we better stop. That's the limit. Don't go any higher than that, my thing is going to break. Now, is it going to break? I don't know, depending on what you're using it for. But that's where it is nice, at the top of that linear range, whether you get to 2 millimeters of stretch on this 1,000 millimeter bar, or 58,000 pounds, then we have to, hey, something broke. Now, let's do a factor of safety. So we're going to do a factor of safety of 2. That means half of 58 is 29,000 pounds, and then half of 2 millimeters is 1 millimeter. So now I can hand you this steel bar and say, hey, we're going to use this steel bar, but we want a factor of safety of 2. So I'm going to say 29,000 pounds is all you can put on that. And just for what we're talking about, and it's cool with steel, is like, let's say we're, in this demonstration we're tensioning it. We're putting this steel bar in tension. Cool thing about steel is you can put it in compression and it's still going to be the same number. You can put 58,000 pounds in compression or 58,000 pounds in tension on a steel bar. Alright, and this keeps our factor of safety of 2, but I can also give you this steel bar and say 1 millimeter. Again, that's going to be hard for you to visually see, so maybe we do have a little gauge that has a readout and a little microphone in your ear to keep telling you, like, what, if you are going to load this, it's going to always tell you what that distance is. 0.5 millimeters, 0.75 millimeters. Hey, 1 millimeter, hey, we better stop what we're doing. And then also, let's say on this gauge, you have a force readout. It's going to tell you the force, you know what I mean? It's going to tell you this force that you're pulling with. Cool. So that readout, maybe in your other ear, is saying 10,000 pounds, 15,000 pounds, 20,000 pounds. How about 29,000 pounds? We better stop, because that's we want our factor of safety of 2. We don't want to get anywhere close to getting to the max. Cool. So this is material mechanics in a nutshell. I think more people, I think most people know that if you hand someone some material, they're going to be like, hey, how many pounds can I put in this? How many newtons can I put in this? We're just using pounds from America. That's what we're familiar with. Anyway, I don't think anyone has any association with something changing in length. I don't think anyone has an association with something changing in length in a linear and a very tiny amount. These changes in length are tiny. I don't think anyone really has an idea that once you passed that value of a tiny amount that's linear, that you get into this plastic zone. And I even forgot to say that if you go up to 58,000 pounds, you're still at the top of that linear range. And then if you back off all force, what happens to your steel bar is, yes, it started here. It stretched that 2 millimeters, so now it's here. And then you backed off, and then you took the tension away. The wild thing is every molecule, let's say these molecules were in this location. You stretched them. They definitely stretched out. They're definitely in a stretched location. When you untension it, guess what? Every molecule goes back to that same location. So it's kind of the magic trick of linearly loading materials. And so, all right, hell yeah, we ran out of juice. Okay, so let's see where we're at. Yeah, so as long as you're in that linear range, all the molecules go back to the original location. And that's where material mechanics, what should comes first is like a very brief and up-to-date idea of what's happening with all the molecules. And so I will say this, because rubber bands, because what happens is that this is linear. And what we know about molecules is usually they're connected with electrostatic forces. We have some electrons for steel. We have a sea of electrons where you have the molecules, and the molecules have, they're kind of positive, I don't know if you call them ions or whatever. I'm really bad at chemistry. But anyway, so you get this relationship, and oh, is it the fact that two of these need to share an electron? Is that why they're kind of attracted? I don't even know. But let's just say we get magnets. So let's just pretend that these are just kind of magneted to each other. So you get two molecules that are magneted to each other. What happens with electrostatic forces is that if you move the distance, what happens is that the force drops off with the inverse square. But what we see with materials is that we have a linear relationship. And so with our steel bar, if I put zero force, 0 pounds, I'm not going to see any change in length. Cool. And let's say I put that 58,000, I'm going to see that 2 millimeters. And then let's keep going with this. Let's say I just do half the load. Let's say I put 29,000 pounds, I'm going to see 1 millimeter. Half of 29,000 pounds is 14,500 pounds. If that's what I'm going to apply, guess what? I'm going to see a half a millimeter of change in length. You know what I mean? And from our diagram, you know what I mean, these are maybe two electrical readouts saying, hey, You just put 14,500 pounds, and this thing's stretching 0.5 millimeters. Let's go back to this 29,001 millimeter. Let's drop a 0. Let's say I put 2,900 pounds. Well, this thing's only going to change in length by 0.1 millimeter. And so on and so forth. If I put 290 pounds on this steel bar, which can take 58,000 pounds, still is going to move in a proportional amount of 0.01 millimeters. If I put 29 pounds, it's going to move 0.001 millimeter. And it's so wild, 2.9 pounds, 0.0001 millimeters, and this will happen. In a classical physics sense, this exactly will happen. There's no point where you need to actually put a critical amount for this to even move. You go take two people and push on a tank. You know, I mean, that's kind of a cool visual that I've been talking about, is that tank will shorten. And so that's one person on one side, one on the other. You double the people and then have two on one side, two on the other pushing on that tank. You just shorten the tank twice as much as if you just pushed on it with one person. I mean, the change in length of the tank is insignificant, but measurable. You know, maybe using electric methods. Cool. 2.9 pounds, add another 0. And yeah, I can't stress this enough, that if you put any force, you're going to see a change in length. And even if we put this max force, 58,000, and got the 2 millimeters, again, that's very imperceptible. Might not be able to see that, and that's the bummer about material mechanics. It's not so easy just to hand you a chunk of material and say, yes, it's got this strength and force, but also it's got this change in length, and you can be a pretty good, idea, you know what I mean? Like one, you can be like, I'm loading it, I see, like I'm loading it with a car, I might know how much a car weighs. But again, you're not going to be able to see 1 millimeter of change in length, 2 millimeters of change in length on a 1,000 millimeter steel bar. You know what I mean? So that is the bummer of material mechanics. It's this cool property that we have to use for all derivations and all, you know what I mean, pretty much everything in material mechanics, we have to use this change in length. This is a very important quantity. And a very important property. And again, the nuts and bolts of material mechanics is if I hand you some material, there's two things about that material that are synonymous. You know what I mean? I can either say you can put 58,000 pounds or you can stretch it 2 millimeters. Those are the same physical things that are happening to that steel bar. So, if you have this steel bar and you find a way to stretch it 2 millimeters, the only way on earth that you can stretch this bar 2 millimeters by touching the external portions of this steel bar from here and here is to put a force on the external portions of that bar of 58,000 pounds. That is the only way that you're going to attach something to that end and make this change in length by 2 millimeters. Alright, hell yeah. And now we're going to finish our kind of derivation of the intro to material mechanics. And it's like, well, didn't you say electrostatic forces drop off of the inverse square, so why is this linear? And I think the best way to show this is the rubber band. A rubber band has polymer molecules. I'm just making that up. But anyway, it's got molecules that might look like that. Maybe they're, you know what I mean, they're wrapped up. This is one molecule. That's one molecule of rubber, just the way, you know, like, again, my chemistry sucks. But hell yeah, I think you get it. Now, when we pull on this rubber band molecule, and all materials, it has a linear range. I put 0 force, it doesn't change length. I put 1 pound of force, maybe it lengthens to here. So I get that much change in length. That's 1 pound. I'm going to put 2 pounds. What we have just been saying is that it's going to lengthen twice as much. So if it starts here, we're going to get twice as much. So now this rubber band is going to be to there. with rubber bands, it has a linear range where this rubber band can stretch 8 times. 2, so it can stretch, it can, if this is its, I don't know how you say it, but if this is its length, we can lengthen it. It can go from a length of 1 to a length of 8. So what I should have said for this is, let's say, if I have a rubber band, let's say it takes 1 pound. Let's say it takes 1 pound to double its length, which is taking its length and then increasing it by its length. That's the increase. That's the change in length. Hell yeah. Okay, so if I apply 2 pounds of force, it's going to get to here because it's going to lengthen that amount. The same amount that it took to lengthen 1 pound, it's going to lengthen that again. That's how linear relationships work when it comes to steel and materials. If I put 3 pounds, I'm going to get another one of those. If I get 4 pounds, well, let's go back to 2 pounds. If I put 2 pounds of force, I lengthen it this much. So 4 pounds of force should lengthen it this much again. If I put 8 pounds of force, I'm going to lengthen it this much. If I put 4 pounds of force, I'm going to lengthen it this much. If I put 8 pounds, I'm going to lengthen it this much again. So I'm going to be out to here. Hell yeah. So this is 8 pounds of force. And what we commonly, for rubber bands, is that you can take a rubber band and stretch it about 8 times. So we have 1, 2, 3, 4, 5, 6, 7, 8. And then, once the rubber band, so this is the molecule of one rubber band molecule. After this gets stretched out 8 times, it looks like this. And guess what? It's now like, and don't quote me on this, but I think, let's say it is covalent. And the way it's bonded now, it's like a glass, and don't quote me on this. Glass may or may not be covalent, but glass is very brittle, or it has like you're going to put force on glass, you're not going to see too much change in length. It's imperceptible, it is there, but then at some point it's just going to go break. That's the same exact thing that happens to this rubber band. It just takes you to unwrap it to actually get into that zone of like, okay, now the full molecule is stretched out, and if you put any more force, you get a breakage of that rubber band. And that's very important because I think, and again, don't quote me on this, I've never taken a high-level course on the fundamental, but I'm being inquisitive. I'm saying, well, if it is linear, there has to be some sort of explanation of why it is linear. And, Google AI at least looked up that. And it's because, the current understanding, or my understanding, without trying to mess up saying wrong stuff, is that the molecule or molecules are shifting. But that's it. You know what I mean? When you put force in the linear range, the molecules shift but don't dislocate. So what happens after you get to 58,000, we said we get plasticity, and it'll go back. So if this is a steel molecule, when you tension it, 58,000, it'll shift but then go back to its original location. Every molecule is just magically in the same location. If you pass that 58,000 pounds, maybe this molecule wants to shift here. You know what I mean? So you were here, you're tensioning it, and then all of a sudden this molecule wants to go there. And then when you go back, and now you're tensioning it like this. When you release, hey, that molecule is kind of stuck in its new location. It's a lot more continuous than that, because when we do stretch something 2 millimeters, it'll go back 2 millimeters. If we take this steel bar and stretch it 3 millimeters, well, it's going to go back at least the 2 and stay fixed at 1 millimeter. So there is that aspect of plasticity. But again, for a lot of the derivations, a lot of that you don't have to know, but it is good to know why it's linear. And again, I'm not providing the best explanation. I'm just saying that, hey, electrostatic forces should drop off with the inverse square. Why do we have, something that's getting farther apart, but maintaining, a linear relationship? And it's because I would just imagine it's because those molecules are shifting, but not getting into like magnets where you're just like, okay, I'm holding two magnets here, I feel a force, I'm going to double the distance, I feel a quarter of the force. That's what inverse square would be. But what we have is not that. We just have, yeah, so I don't know. You know what I mean? Again, that's an interesting one. All right, hell yeah. All right, booyah. So we're almost done with this, but we got two more concepts to talk about. And we might break out. Now we got enough room to write. But what I just said is I gave you a 1-inch steel bar and it has a length of 1,000 millimeters. That is a very specific chunk of material that has a very specific strength, you know what I mean, where you can put a force on it. Alright, hell yeah, sorry about that, we're back. And what we've been talking about, it has a length, and that is crucial in telling you that you can get 2 more millimeters out of it. But those two quantities, by handing you a chunk of material and saying it has a force that you can exceed, I think that's intuitive. And then we've spent the entire time trying to relate the idea that the thing changes in length, and that's important. And that's a quantity that if someone gave you a readout in your ear or displayed, it would be synonymous with this 58,000. And you could just chart those back and forth. So I guess there's two concepts. Is one, we do want a chart of those back and forth. I want to say that the number, so I'll start here. I want to say that the number 2 is synonymous with the number 58,000. And almost equal to. How can 2 be equal to 58,000? It's because you're relating two different things. It would be like trading. I could say 1 orange is equal to, I would say 2 apples. You know what I mean? Not to throw apples under the bus, but at school, if you got 1 orange, that's a pretty good ripeness and stuff. Hell yeah. I think it's worth 2 apples. So if you got the 2 apples, you know, you could trade for that 1 orange. You got the 1 orange, you could trade for those 2 apples. And so in this representation, 1 is equal to 2. Cool. It's just that the units are different. You know what I mean? So you can't say that 2 apples are equal to 2 apples. You can't say that 1 apple is equal to 2 apples. Maybe the units would have to be a little bit different. I don't know. I mean, maybe the 2 apples, maybe the 1 apple comes from the cool kid. Maybe it is worth 1 apple. You know, your 2 apples are worth the cool kid's 1 apple. I don't know. But typically it would be because maybe this is a Fuji. And this is a Red Delicious. You know what I mean? So that's important. Same thing here. So what I'm saying is 2 millimeters is equal to 58,000 pounds. And so, you know what I mean? But these numbers, the number 2 is not the same number as the number 58,000. So then what do we have to do to the number 2 to make it 58,000? And that's what we're going to talk about next. And we don't actually just relate both of these. So we have to maybe take one step back to this. Hell yeah. Alright, hell yeah. So we're going to pause on the fact that these numbers are equal. In a sense they are, because we've been talking about force and change in length. But now let's say I hand you a steel bar that's only still 1 inch in diameter. I mean 1 inch in cross-sectional area, like 1 inch squared. That's the cross-sectional area. But now this steel bar is only 500 millimeters in length. How much can we stretch this thing? Well, it's because, and let's go back, and I think it is very useful to be like, hey, there is 1 iron atom, and there is another iron atom, and one of the properties says that if this is the length between 2 iron atoms, I can only stretch this iron, and this iron atom's fixed, I can only stretch this iron atom to there a distance of 0.002 of the length. So if I know what this length is, I take 0.002 times the length, and that's the distance I can stretch. If I stretch it farther, it breaks. If I stretch it up to here and let go, these 2 iron atoms go back to the same location. And let's check our math to make sure that's the same thing we did up here. I use this example because if you start with 1,000, you get a number of 2. And that's the human brain is very good at quantifying integers. So 2 millimeters, I can handle that. I can handle 1,000. What I can't handle is the opposite. If I say this is 1 meter, how much does it change in length? 0.002 meter? And I would do this because you're going to have to use a number this small. And you're going to have to, you know what I mean, say, hey, the length is just one length, you know what I mean, the length is L. And then so this is 0.002 L. And so that's kind of that relationship. But if you start with 1,000 and say you can stretch it 2 millimeters, I think it's easier to say, hey, this is a 1 meter bar, and 2 millimeters, I'm going to move the decimal place 3 times. That's going to be 0.002 meters. And so that's what we have. And if we do the 500 millimeter bar, I can stretch it 1 millimeter. So let's move the decimal place 3. So we got 1, 2, 3. So we got 0.5 meters on this, and 1, 2, 3, 0.001 meter. Cool. The relationship between the length and the change in length, that's what they're going to talk about. See what I mean? And now this is where you might lose your mind. But it's proportional. So if I say change in length divided by length, for this one it's going to be 0.001 divided by 5. 0.5. For this one it's going to be the change in length is 2 divided by 1,000. Is there any other one? And then we could say this is 1 divided by 500. So all 3 of these, this is 2 ways to say that. We can also say this is 0.002 divided by 1. Okay, this one's going to be the easiest. 0.002 divided by 1. It's the ratio. I mean, still, this has units of change in length divided by length. And that's still in units of like meters divided by meters. So this is still dimensionless. It is a number. It's going to be represented as 0.002. It's dimensionless, but it is useful to put dimensions of meters per meter on this term. And then even for things that are dimensionless, but are still a relationship between one over another, it is very useful to take this number and divide it by 1 and just represent it. So if I'm and I don't do that enough, but if I have strain of steel, and this is the max strain of steel, I'm going to say 0.002 divided by 1. And this is representing the change in length compared to the initial length. All right, hell yeah. So now, and then I'm just realizing we need to cover one more topic. Why I start with the steel bar and give you the max is because that's it. That's the max force. So why don't we find that first? If you're building anything, like a bridge or anything, why not take the material and find out what max force you can get out of it, and then see what force you're applying, or design it to take a less force than that with a factor of safety. But the other bummer of material mechanics that definitely gets heady is you're like, well, we're not going to put the max force. I'm going to put 60% of the max force. I'm going to put 40,000 pounds. Now what? If I put 40,000 pounds, how much does my thing change length? You know what I mean? So if I in one gauge in my ear, it's saying 10,000, 20,000, 30,000, 40,000. You know what I mean? What's it going to chirp in my other ear? Well, it's going to now we need like kind of a chart. 0.0. So for this one, 2 millimeters is associated with 58,000 pounds. 1 millimeter is associated with 29,000 pounds. And this is close to 60. This is 30. So what did we have in between? What did we say? 29,000 plus 1450, which is 30. Yeah, this would be a 3, and we get 43. So 4350, would be 1.5 millimeters. So there you go. So if I can only put 40,000 pounds, I can only stretch the thing 1.5 millimeters. Now this is a linear relationship, and it should be like real simple, real easy. And I swear material mechanics doesn't make it easy, because on this one they almost don't use enough math and teach you like the actual graph of this, because what we're graphing is change in length by force. You know what I mean? So I think this is the most useful relationship. This is what we started out with the entire time. I've chosen a 1-inch chunk of steel at 1,000 millimeters. So I can make this relationship. I can say if I put a force of 58,000 pounds, I'm going to get the max change in length, which is 2 millimeters. And this is the line. And instead of being a line that goes on forever like a continuous mathematical function, there is a range here. And this is also a good thing for all physics problems. Would it make sense to put negative force on this? Well, honestly it would, and I've never done this before, but you could do the graph the other way, equal amount, because then you could say the change in length is squashing in. You're going to get a negative change in length. If I put negative 58,000 pounds, we already talked about that compression being the same, but that's your limit. I'm going to say if you put more load on this, well, one, you get into the traditional graph, and then it goes like that. It gets actually stronger. You get plastic to form, and then it gets stronger, but all that is heady as hell. Whereas just like you're going to be in this linear window anyway, trying not to kill people. Booyah. All right, hell yeah. So from this is an equation. You know what I mean? Like any algebra, you know what I mean? This is basic algebra. What's the equation of a line? Y is equal to mx plus b. So let's do it. You know what I mean? So we got y. Y is our dependent variable, and that's going to be our force. So we basically have force. That's our y variable. Our x variable is our change in length. You know what I mean? And cool. And then the route that we're going is like, hey, we can find the slope of this, but we need to find the slope. We need to do another graph that's stress and strain. And this is where I failed. This was like second day stuff, and I was just like, I'm failing this because of those terms. See, it doesn't that just make you like go from, oh, I get what's going on. This is just a force. This is a change in length. I get that. And then we're going to go to here. And all this is just, hey, force divided by the area, cross-sectional area that I gave you. And then all this is just the change in length, which were divided by the original length. So it's not that big of a deal. But these Greek symbols suck, and they're difficult to look at. All right, so this one, let's get our equation. So we have slope plus, this is the y-intercept. It goes through the origin, so this is just 0. So even from an algebra standpoint, this is getting easier and easier. So now what's the slope? The slope is just rise over run. Cool. So let's not mess it up and say it's run over rise. Don't do that. Which is easy. That's the easiest thing to do, because if you're going this way, like reading a book, I would want to go this way and then that way. But that's run divided by rise. I mean, I can say this distance is 2 millimeters, but that's the bottom part, 2 millimeters, that's the run. And then the rise is 58,000. So now I have this equation for force and change in length, which is y in force is equal to 58,000 divided by 2 is 29,000 times x. And x is going to be measured in millimeters, and the force is going to be measured in pounds. So we have an equation relating to two different things that don't have the same units. But that's where this slope does have the units that match. This slope is pounds per millimeter. So if I'd put pounds per millimeter here, then these units will cancel, and then we're just left with pounds. But even this is almost the first graph that should be taught first. And so now we're going to run out of room. But the reason why they don't double down on this is like, well, what happens if I give you not only a steel bar that's 500 millimeters, so it's half the length, but then is only half inch by half inch, and the area is 0.25, a quarter inch squared. Now the question is, now what? So, if we had that 1 inch steel bar, we got this number 58,000. And it could be obvious that, you know what I mean, I'm trying to pull on both of these. You know what I mean, this is the obvious part. This is just a quarter the strength. So it's going to be half is 29, quarter is 14.5. So this steel bar, I can put a tension of 14,500 pounds. Why? Is because this cross-sectional area is a quarter. Like I gave you a quarter of the material. And this is where if I'm pulling tension, length is irrelevant. Like this, the force that I can apply to a steel bar, the max force, is not a function of the length that I give you. Now, the change in length, when I apply that max force, is a function of the change in length. The change in length is going to be, you know what I mean? So how do we relate this? If I put the max force, that is going to be synonymous with the change in length max. And we've talked about this with a steel bar, that if I put the max force on a 1,000 millimeter steel bar, the max change in length is 2 millimeters. Cool. But we're going to see that if I put the max force on this new steel bar of 500 millimeters, its max change in length is 1 millimeter. So for this video, I've just been giving you that relationship. You know what I mean? And that's something that we would just observe. You know what I mean? So that is the, hey, I took a material, I'm pulling on it, and I'm measuring those change in lengths. We find out that it's linear. That's cool. Maybe use the rubber band example of the molecules just shifting before they kind of get into that electrostatic inverse square relationship that potentially molecules should be in. You know what I mean? Again, anytime I use chemistry words, just probably ignore what the hell I'm saying. Alright, hell yeah. So this is the discrepancy. I gave you, in both cases, a chunk of steel. The same material, and we're getting two different numbers. The max change in length is going to be 2 millimeters there, and 1 millimeter there. And I'm getting two different numbers for the max strength. The max strength is this number, and the max strength for this one is this number. So this is the simplicity of material mechanics, but I swear it's the hardest jump even for me, like almost every time. Is that yeah, so here it is. We need a number that's the same for both of these. And what's that going to be? Which one should we do first? I think it might be easier to do the change in length. We said this was a change in length of 2 millimeters because we started with 1,000 millimeters. And then this was a change in length of 1 millimeter because we started out with 100. So then we're going to have a relationship between change in length and the initial length. So if I say the change in length here is 2 millimeters and the initial length was 1,000 millimeters, we get this relationship of 0.002. I could also flip this on its head, you know what I mean, L divided by change in length. That's going to be 1,000 divided by 2, but I mean, we don't do that, so let's just not. But you get this relationship. Change in length, and again, this is a number that's dimensionless, but it's still relating two things. So write it as divided by 1, and that's very useful. Almost like gravity, you know what I mean? This is kind of from the differential calculus perspective, or derivative calculus, is if you have the acceleration of gravity g, let's just call it 10 meters per second squared. It's a horrible way to write it. I write it as 10 meters per second. and then per second. Even if I just do the units like this, it's helpful. So we're going to do that same process. We're going to say this is 10 divided by 1 meters per second per second. So now we can see that this is 10 meters per second per 1 second. And now we can see the relationship. It's a change in velocity divided by the change in time. Just like this is a change in length divided by the initial length that we're given. So it's still a relationship, and that's very useful to take that number and make it into a proportion just by dividing it by 1. That's very visually useful. All right, hell yeah. So no matter what length of chunk of steel I give you, if now I could have a device on it, you know what I mean? I put a device and you got it into your ear and it beeps. And it beeps when you lengthen it, where we get into what I call that break point, loss of life point. But it sucks from the intuitiveness of material mechanics, because it just means that you're at that top of that linear range. You're ready to go plastic, ready to go stronger, and then ready to almost crash and die, kill everyone. But if you're here, there's a hell of a likeliness that you're going to be there before you can fix things. You know what I mean? So that's the deal. So once you get to the top of that range, and I say once we get to the proportion, so I hand you any length of, you know what I mean, and this thing's beeping in your head, what you can do, let's say we just have, anyway, it's going to beep and say, hey, that's the limit, and then you can go measure the change in length. And when you go take that measurement of the change in length, you can compare it to the initial length of the steel bar that I gave you and divide those two numbers, and you'll get that number every time, because this scenario was trying to max out that linear, you know what I mean? And that's the other thing, again, the crappy thing about material mechanics is that's just one scenario. I could have stretched this thing out just a little bit and then beeped in your head for you to go measure. You go measure, and you realize that that measurement you took divided by the initial length is 0.0012. Cool. That's less than 0.002. And all that means is that we're not maxed out. You can put more juice into this steel bar. You can tension it more if you want to, unless maybe your factor of safety is 2, and then so now you're actually over. You know what I mean? So those relationships are a little bit harder to see. I think it's a lot easier just to be like, hey, there's a max involved, and this is the relationship for that max. And we call this change in length divided by initial length of 0.002 for steel. This quantity is the strain symbol. This is normal strain, and we can say normal strain max. Even though for this is still a normal strain, it's just normal strain whatever. You know what I mean? We put whatever force on that we were wanting to put, and that's what we got. It's still a change in length whatever divided by the initial length. And that is where applying little symbols to, you know what I mean? So that's why I always start with force max to get a change in length max. Then we can get an equation. You know, because if I put 0 force, and then I'm going to get 0 change in length. Cool. That's going to be force min is 0. Change in length min is 0. Cool. And then I'm going to have a linear relationship of any numbers in between. Does that make sense? And so I'm going to have force whatever that I put on it, and I'm going to get a change in length whatever. Now, it's not whatever, because I have an equation for this. I know exactly what the change in length is when I put whatever force on there. And then, so this gets to be like force design equals change in length design. When I apply the force design on this bar, I'm going to get a change in length, and I'm going to call this the change in length design. But it's just way more easy to like know what force you're putting on than to know what it's changing length and then stopping at that location, compared to designing it where we're just like, well, I know I got a bunch of weight and it's within that force design, and so we're good to go there. And then you might have a couple more. You might have force allowable You might have force design and then force allowable. Maybe you got this little window between, hey, we're kind of shooting for this, but we're allowed to go a little bit higher. You know what I mean? And so this is our true factor of safety of 2. This gets into a factor of safety of like, 1.5. And then we got to quit because we don't want to get anywhere near force max. And what this whole time I've just said force max is the top of the linear range. And this is where right here things just go plastic. Even just for a little bit for steel. It's like you didn't put any more force on there. And it's just moving, baby. And then what happens to the molecules is they actually have voids. And when we stretch it, this thing might get thinner, but it fills in the voids. And so it's almost like cold forging. You get a stronger product. It got hella thinner, but you do get more strength out of it, even though it got thinner. And then because if you just started with that material, which is thin, measured its cross-sectional area, it would be maybe 0.8 inches squared, less than the 1-inch steel bar, and I'm getting a higher max. So both those things are going on. And so, there's the other aspect that, hey, the force actual is kind of double. It's instead of 58,000, I can put 100,000 on there, given the area. But if I'm already starting with 1-inch steel bar, doing all that process, I've already killed people. You know what I mean? So because I've got past this point. But I'm just saying for the acronyms, this could be force yield, force Y for force yield. And this could be force P for force plastic, is that what they say? Or proportional limit, they call it PL. This is the proportional limit because it's just a straight line, even though for steel it's kind of short-winded. And then we get into here. This is the ultimate, force ultimate. And then that's it. You can't design into that range. Alright, hell yeah. So then I guess the last thing is to get that number for force. We've been talking about force is equal to 58,000 pounds. And then that means an area of 1 inch. Cool. And then so I said if we did an area of a quarter inch squared, we were going to get a force of a quarter of this. 29, half of 29 is 14,500 pounds. If I have an area of 0, I can put a force of 0. If I have an area of, if I have an area of 1/10 of an inch squared, cool, this goes to 5,800. And again, we have that same same deal where it's just like this number and this number. I want these numbers to be the same. And so we need a relationship, and what we do is we do force divided by area. And we see this is 58,000 divided by 1. Cool. 58,000 pounds divided by 1 inch squared. And we get 58,000 pounds per inch squared, which is 58,000. Alright, hell yeah. Sorry we cut out there. But this term is 58,000 psi. But this is the relationship, and again, it's relating to terms. It's not just pressure per se. It's 58,000. And this is another one divided by 1 because we have 58,000 pounds divided by inch squared. This is a much better way to say it. But there is a very usefulness. If I have a basketball that's filled with 10 psi, what that means is if I stand on this basketball, which is really cool, let's say I weigh 160 pounds, what's going to happen is I'm going to make an imprint on like a sheet of paper or the ground of 16 inches squared. So whatever the circle that has an area of 16 inches squared, that's what's going to happen because the PSI is matching that. And this happens with materials, so it is kind of useful to be like, hey, this is a strength. Train tires, I haven't posted this video. This is the first video I made. And it should go viral, but anyway. Train tires are pumped up to 150,000 psi. So you can do all those things to steel to actually get 3 times the strength. Just common steel is going to be 1/3 of the, you can only get steel to be 3 times stronger just per se. You can buy grade 8 bolts and you actually can get this same steel. But train steel is this, and it's the same thing as 150,000 psi. So what this means is that if I put 150,000 pounds on this one wheel, you're going to get a contact point, a contact patch that flattens of 1 inch squared. And what do we know about a wheel is that we get a contact area of a dime. And the wild thing about a wheel, wheels are 2 inches in width. And then so it actually is like almost 2 to 3 millimeters. That's what you get. That's the contact patch of a train tire, and 3 millimeters is actually skinnier than that. And if I'm getting this wrong, it's 2 to 3 dime thicknesses. So 2 to 3 dime thicknesses over 2 inches is the area of a dime, and a dime is much less than an inch squared. I don't know if it's a third or a quarter or a fifth or a third, but you get the idea. And that's relating this idea of PSI. So I do like this term. I do like to say that this is the strength. So we talked about how the force, 58,000 pounds, is the strength of steel. Well, I can say, I can get there, and this term gets this, is a sigma. So sigma is the strength, and this relates this 58,000 pounds per inch squared. Throw a 1 on it, but that's that relationship between force and area. And now I should help myself out. If I call this the strength of steel, I can still call this the strength of steel. It's just the change in length, which is the same thing as loading something up with force, to reach a max. We just talked about that. It's the same thing as just loading something up until it changes length a specific amount. And then so we have this relationship between the change in length. And on this, this proportion is always going to be the same. So let's go through that. So if I have 14,500 pounds divided by 1/4 inch squared, the 4 goes upstairs and we get that 58,000 pounds. The only one that's not going to work is this. But if I have this, 5,800 pounds divided by a tenth. Sorry, bummed that out. But at 1/10 of an inch squared, 10 goes upstairs, and again I'm back to that 58,000 pounds per inch. You know what I mean? So even though I'm taking two parameters, that's like force max divided by the area, this one is going to be the force max. This was force max for a 1 inch steel bar. This was force max for a 1/4 inch steel bar. This was the force max for a 1/10 inch steel bar. So, and again, this is the symbol I'm using, so this has to be the change in length max, or the strain max, which is change in length max divided by, I'm sorry, no. Sigma is the strength, is the force divided by area. And then the qualifier on this, or the subscript, we can say is sigma max, because we're using force max. Now there's no area max, I'm just giving you some material that has area, so there is no subscript on that. But those are related. And then again, I can just give you, I can give you that 1 inch steel bar, and then you could just say, well, I'm just going to put a force whatever. And it still has that same area. Area didn't change. And what you're going to get is you're going to get a strength whatever. And the same thing. This isn't just like a whatever number. It's the whatever force you put, a number in pounds divided by that area. And that's what you're going to get. And as long as we're not breaking people, then, this number can be between 0 to its max, 58,000 psi. And again, divide by 1 to make it into a ratio. Hell yeah. Alright, so I forget if we already did the normal stress. I mean, did we do that? Did we talk about how this, and it's good to do this one again. How about strain max? Normal strain max is the change in length max divided by the initial length. Again, there is no max symbol on this subscript because I just gave you a length. Cool. But I could say, strain whatever is equal to change in length whatever. So if I divided by the initial length. So if I give you some sort of length and we're going to have a little device on it, that reads out a display. We're gonna change its length, obviously by putting force on it, and we're going to measure that change in length. And so we're going to have that change in length divided by the original length. And this number is just going to be, you know what I mean, 0.0, let's do a different one. 0.0, instead of 0.002, we're going to go 0.0008. You know what I mean? So this is smaller than 0.002. That's the other thing, is you're already starting with small numbers. It's hard to see that, you know what I mean, this is the max. This is actually the biggest it can be. And to make that smaller, you know what I mean, you got to throw an extra 0 maybe, you know, bring it down to a 1, a 1.3, you know what I mean, an extra 0.8, an extra 0.4, you know, you throw an extra 0.2, and this is just 1/10 of your change in length. So just to be able to kind of see that aspect. All right, hell yeah. And now we better break it, we better bring it home, because let's try to graph this one. And then what we're going to do is we're going to graph strain and stress. So this is kind of bringing it home. I said that and we're going to go a quantity of 1, half, quarter. I'm going to say this is 0.002. This is the max. This number represents the max. This 0.001 maybe just represents factor of safety of 2. You know what I mean? And then just, hey, this number, 0.0005, is just whatever. You know what I mean? I'm just changing the length by whatever. And then what we're going to see is that it doesn't matter if I gave you a 1 inch by 1,000 millimeters or something smaller and then something narrower. As long as the material is the same. This is steel, this is steel, this is steel. What we're going to have, this is the relationship between force and area. We said if we're given a 1 inch area, we can give 58,000. And that's a pretty good one, because if area is 1, well, that's actually, when area is 1, these two numbers are going to be the same. Force in pounds is going to be equivalent to the strength, and this is called stress. So this value is stress. I like to think of it as strength, though, in PSI. And this is strain. But I like to think of it as stretch. You know what I mean? Because I'm always wanting to say that this is synonymous with force, which is very synonymous with strength. And this is synonymous with change in length, which is very synonymous with stretch. So, and stretch and strength both are S terms, and strain and stress are both S terms. Strain and stress have to be the two dumbest names that you could name these things, because you're already turning them into proportions where you lose the idea that they're force and stretch. Stress and strain, it's really difficult for beginners to, you know, even mentally hash those two into their brain. All right, hell yeah. But we can do it. So we have this high value of 58,000, and we said this is in pounds per inch squared. But we said if the area is 1, that's our max, and that's going to happen when we get to this value. Booyah. And then if we said we have 0, it's going to be 0. If we said we had the halfway point, what was the strength at the halfway point? Did we? Well, we did the quarter. Well, we didn't do that one, but yeah, if this is 1 square inch and we get 58,000, if I do a area of a half an inch squared, then we get 29,000. Cool, pounds. Cool, and then so the area is 0.5. So if I do this little equation, the force is 29,000, and yeah. Oh well. Yeah. Oh, I'm messing it up. That gives you this value of the max. If my force is 29,000 and divide by 0.5, that gives you this value. So now this is the max, and I think it is very useful to figure out what the max is. But now we have to just say, like, well, what if I put 0 force? Well, I get 0, you know, this quantity, and then I get a linear relationship if I just put whatever. You know what I mean? So if I change the length by this ratio, yeah, anyway, so that's linear. But yeah, it sucks because you're saying this is a quantity of change in length divided by length, and this is a quantity of force divided by area. This and it seems like we just talked about how this doesn't change. Well, no, we can find the max value, and the max value will be the same no matter the shape that I give you. It doesn't matter what the shape of the chunk of steel I give you, it's going to obey this number. The change in length will be the change in length max divided by the initial length will be this number. But then I can just not change. I can just change the length, not max, but divided by 2. And the initial length didn't change, so that gives me this value right here. But if I only change the length by half the max, well, then that's... And this was the area of 1 square inch, and if I could tension it, I could do 58,000. And those two numbers are synonymous, 58,000 pounds and this max change in length. You know what I mean? Then if I only change the length by half, then this number drops to 29,000. But again, I could have any area here. It doesn't have to be an area of 1. And that ratio of the force, like force max, divided by the area, is going to be that value. But if I only change the length by half, then the force max is only half. So those two things are proportional. That's the whole idea behind this idea of Hooke's law, that a material, and it's this line right here. And this works for any material, doesn't matter the length or the area. The max ratio is going to be this value for steel, and then the max ratio of force divided by area is going to be this number 58,000. So we've spent a lot of time talking about how this number is 58,000 pounds. Now this is a ratio of pounds per inch squared. And then we've talked a lot about how the change in length was 2 millimeters, which is 0.002 meters. But that was only if I gave you a length of 1, you know what I mean? A length of 1 meter, or a length of 1,000 millimeters. This 58,000 was when I gave you an area of 1. But if I have a length of half a meter, or an area of 1/2 an inch squared, these ratios remain the same. And hell yeah. Would end it on a confusing note. But no, we got to be done with this. But hell yeah. So that's it in a nutshell. This is the whole reason. Going back to the whole reason. This is why I like to be like, hey, I can give you, and I do this mentally for myself. I'm giving myself this 1-inch steel bar, and I'm going to say to myself 58,000 pounds. I'm going to say to myself, and it's 1,000 millimeters, I'm going to say to myself 2 millimeters. Cool. This is my basis. But then when I go buying, I'm hardly ever buying a 1-inch by 1-inch steel bar. You know what I mean? That's too much to work with and weld with, and you know what I mean? But when I go to I might buy 1/4 inch. You know what I mean? Just, hey, these are useful. 1/4 inch, and hell yeah, I might be using a meter. You know what I mean? So we got 1,000 millimeters. We have a 1/4 inch by 1/4 inch. This gives me an area of 1/16 inch squared. So now what I'm thinking is I'm just going to divide this. I don't have an inch. I have 1/16 of an inch. So 58,000 divided by 16. I know that this can take a tension of 3,625. That's way more useful than saying, oh, I know it's steel, which has a max of 58,000 psi. This is force divided by area. And if I want to solve for force, I just multiply this number by area. That's one step. That's one step in the right direction. So 58,000 times 1/16, is essentially the same equation. But I think it's easier to be like, if I had a 1-inch steel bar, 58,000 is the number. And again, the reason why I'm doing that is because this strength is a force divided by area. You're just going to pop out a number. What we want to do is we want to take that number, divide it by 1. And the whole reason I've been doing this is because I get an area. I'm going to start with an area of 1, and then I'm going to say the force and the strength are synonymous. Same thing with strain. Strain is change in length divided by initial length. You're just going to get a value, whether it's the 0, whether it's the whatever number, or the max number of 0.002 for steel. And I'm going to take that number and just divide it by 1, just to make sure I know it's a ratio. But if I'm starting with a length of 1 meter, or an equivalence of 1,000 millimeters, then I kind of know that this, well, especially with 1 meter, whatever this number is, 0.002, then I know that is the that this number represents the change in length. You know what I mean? And make sure you have a subscript on this, because are we talking max? Then this number applies. If we're just talking whatever, then this number could be whatever number between 0 and 0.002. But still, hell yeah, that's still a lot. But again, I hand you a chunk of steel, change in length, force. You know what I mean? And then let's make them, and that's why I think it's pretty cool. Start with a 1,000 millimeter bar with a area of 1 inch squared. And I know this value is not 1, but you can make it 1 meter, and you can get that 0.002. That number sucks. That's why I use 1,000 to get 2 millimeters. It's just an integer, and it's easier to see that ratio. Alright, hell yeah. But, you know what I mean? It's still, this is the crazy thing. This is just day 1. This can be a day 1 lecture, and it sucks. You know what I mean? But we have an idea that a material has strength because we can apply a force, but we definitely need to know that we're going to change its length. And tension and compression are the first places to start. The next thing that we do is the only other thing you can do to a chunk of metal is take a bolt and then shear it in 2 by pushing down and up, you know what I mean, like that. That totally sucks. The geometry almost is nonsensical, and you know what I mean. But you can still get similar numbers, and you can still get a similar idea that if I'm applying a force, it's going to be V now. I am, you know what I mean. Hey, there's going to be a V max, and then what's our change in length max? Well, when we shear something, we're actually going to make it look like a diamond shape, or it's going to turn into that, and we're just going to measure that angle. That angle is small, and then so it's totally related to this kind of change in height anyway. So hell yeah. But that gives you the lead-in of how we want to do the same thing with shear. We want to say that shear is just, hey, a force. You know what I mean? And it sucks that they even changed the letter on you. You know what I mean? It's a V for force, which sucks. It's still a force. But we're going to have, hey, some sort of max. And then we're going to get some sort of, like, hey, it didn't break yet, but it's starting to do this. And guess what? When we do this, or however I have this drawn, when we do this with it, well, these are opposite drawn. But anyway, when I do this with it, and put a force on it, to the max, the same thing is going to happen. If this is 4 molecules of steel, I let go of that force, these molecules go right back to the same original location. So that's the magic trick. That's the linear range. If I put 0 force, there is no diamond shape. If I put half the max, V max, then I just get, you know what I mean? The diamond shape is just half. You know, it hardly did, or it just did this by half. If I put 1/10 of the force, then you're going to get 1/10 of that tiny change in angle. And because these angles, again, are small, if I measure them in radians, I just take this length right there, multiply it by that, and then for this, just to know your max, we're going to use this. This is our angle, and instead of this normal strain being a change in length divided by original length, we're going to say that, and this is going to be the same number. 0.002 is the max number for whatever size chunk of steel. Same thing with shear. The max angle, whatever size chunk of steel, can only be 0.004. And so maybe you can remember those numbers, it's just twice. You can do a little proof to see why it's just twice. But then there you go. And so, and you can even take a little chunk of steel. This would be a difficult one to do, but again, if you made that angle, that's the max, and you could figure out what height you would see if you, I don't know, took a bolt and then started doing this and that to it, and then this was your exposed visible, little thing that you could see. Maybe you could see, that would be a difficult thing to measure. That's what sucks about material. How the hell are you going to measure that angle that you can't see anyway? You can't even see that angle, so how are you going to measure it? Well, again, a little gauge with a little readout and a little alarm in your earbud that says, hey, stop. You just did this, you killed people if you go any higher. But if you stop right there and go back, every molecule goes back to the original shape. So hell yeah. And, if you want to actually measure that angle with a little protractor, you can, because we just have this distance here. Or if you want to know the height between like what you're doing, yeah, that's more. If you want to know the height change right there, well, it's just that angle times this distance. And yeah, then you just use a little bit of small angle theorem. Sucky. Yeah, but sheer sucky. So why did I even go that? Just to say that it just gets worse. You know what I mean? It just gets more hella confusing. But we try to take something like this and make it simple. Sorry to end on the shear confusing note, but that's how I failed. Just because I didn't understand shear. But that's why we really want to start with the fundamentals of why the two nuts and bolts of material mechanics is something. I give you a chunk of material, you can yank on it so much. We all get that. But it's synonymous with how much it's changing in length. It just sucks because you can't see it, hardly, and you'd have to have complex electrodes to measure it. You can measure it with the strain gauges, though. I have never owned or seen, even graduating college, no one ever showed me a strain gauge. Like, that would be useful, right? Anyway, we are done. Voice is cracked. So, hell yeah, that's an introduction to material mechanics. I think that's the best one I've ever done. You know what I mean? And that's just what we do. This is not even what I wanted to do. A student's just like, hey, can you do this other proof? And I just have mental illness, man. Like, and just a need to, if you're going to mention the words material mechanics, and then mention the words force, strength, change in length, strain, it's just like, I don't see why, like, it's difficult for me not to do this lecture every single time, but I think this was probably the best video on it, so I can just be like, hey, watch this video, and now I can move on. But it's just like, I feel like I can't move on until I've kind of found a mastery in teaching, and so that's where I'm just kind of honing in, and I always use kind of like one simple example. Because like I said, you can take this, and then you can just modify it. You know what I mean? It's the perfect visual for me. Make your own if you want, but it's the perfect visual because it involves that area of 1, and it kind of involves a length of 1, but again, it's 1,000 just to get an integer value of that change in length, because again, change in length suck. If I said this was 1 meter and this was 0.002 meters, you wouldn't have a friggin' clue. But the other aspect of that is useful is that this 2 divided by 1,000, again, that's 0.002, sucky. But you can also, and this is change in length, put a 1 under it. It's change in length divided by original length. This is the last thing we'll do, is that you can easily just multiply by 1,000%. This is a proportion which people have a hard time with. But if you multiply by 100%, then it's 0.2%. So if I give you whatever length of steel, hey, I can lengthen this 0.2%. Now that still sucks. It's not an integer value of a percent. But still, I think that gets closer to, I could probably figure that out. You know what I mean? You'll probably mess up the math, or I would, but, 1,000 millimeters, what's 0.2% of that? Don't know it. What's 2% of 1,000? Maybe that sucks too. What's 100? If I have 100 millimeters, what's 2% of that? That's 2 millimeters. Okay. So if I have 1,000 millimeters, what's 2% of this? That's 20 millimeters. Well, guess what? We're not doing 2%. We have a suckier number. It's 0.2%. It's a tenth of that. You know what I mean? So you do you. But I think that is very useful to know that the max, and again, this is strain max. Always put a little identifier, a little subscript of what the hell you're talking about. Because you could do a strain of 0.1%. That 0.12% we were talking about. That 0.08%. And you have to, that's the sucky thing, because once you get to the problems, you're just like, ooh, now this looks awful. Like, I don't, you know, I have a hard time relating this number to this max number. And just know you can even go lower. You can go to 0. Temperature variations are like 4 zeros maybe, and then like a 1 4. You're just like, oh, that number sucks. You know what I mean? Move the decimal, and don't quote me on that, but it could just be 3 zeros and something going on. But hell yeah. Alright, so we have thoroughly, I'm done. But thanks for joining me. This was, I thought this was a good one. So, booyah.